Let it be. So you have understood these things, all of you. Should we move ahead and see the next slide? The next slide talks more about these two heuristics. Now, if I want to know which heuristic is better than the other heuristic, how do I actually understand it? Okay, so we can understand it by looking at. So first, we need to understand that both are the heuristic that we are trying to compare or trying to identify which one is better than the other. We need to figure out whether they are admissible or not. Once we know that they are admissible, they will be gradually collapsing to zero, because naturally it is going to be an increasing or decreasing order, okay, function. So the next thing that I need to do is, for every node in my state space, I would actually calculate value of h2, value of h1, and I will see if whether the values are increasing or decreasing. So for every n in my state space, so I may have certain finite number of nodes in my state space, and sometimes the state space is going to be very large. So identifying these stuff and finding out which heuristic is better than the other is a very challenging task in itself, because the state space for certain formal problems can be manageable, but otherwise the state space can soon or actually be very large, and in that case this is not advisable in general. For the first 3 points that we are talking about in this slide, to find out which heuristic dominates over the other heuristic, means which heuristic is going to be better compared to the other heuristic as far as the search strategy is concerned. Now here they are demonstrating how exactly to prove empirically, means based on evidence, based on experimentation, how to prove that one dominates over the other. Now we see that we can observe that by looking at the heuristic value h2 and h1 for all the n nodes in the state space. We could observe that h2n is always greater than h1n. Okay, then we can say that h2 is dominating over h1. Again, how to prove it? So to prove it, we will actually do the searching by by giving in random initial and random final state combinations. So what will they do is, they will actually randomize one start state, randomize some goal state, put your algorithm to practice using heuristic 1, put your algorithm to practice using heuristic 2. Remember how many nodes were expanded. Okay, how many nodes were expanded, typical search cost. So do note search cost, do it repetitively again and again by randomizing these process. Okay, identify what is the depth of the solution, identify how many nodes required to visit in order to reach the solution on an average. Okay, so then you will find that A star with H1 heuristic, you require 227 nodes to reach your solution, and H2 heuristic required 73 nodes to be inspected for a depth of 12. Similarly, by changing the depth to 24, so we'll be actually generating problems that will get solved by a goal node lying at depth 24. Means we can only reach to the solution by doing at least 25 moves of the space. One move, you can understand in the 8 puzzle problem, one move mean going one step down in the search tree. So 12 deep search tree means, or the solution lying at depth 12 means, at least I need to follow, or I need to do 12 steps so that I get the goal node. Okay, depth 24 means a solution is lying at depth level 24. That means 24 स्लाइड्स के बाद ही या 24 ट्रांजिशंस के बाद ही मैं कॉन्फ़िगर कर सकता हूं गोल नोड को, ऐसे प्रॉब्लम्स. ओके, एंड प्लीज सी दैट दे हैव नॉट एक्चुअली काउंटेड इट, बिकॉज ही डेप्थ लेवल 12 का जो number of nodes that are inspected, that is 36,44,035 nodes they had to navigate, keep in the memory, and that's why this is memory intensive, we said. Now replace this sliding problem with a larger state size. इसमें state size limited है, 9 bytes लगते हैं मुझे. 9 into say one location is one number, right? Number means maximum 4 bytes. 4 bytes into 9, 36 bytes. 36 bytes into 36 lakhs 44,035. So that much amount of space you will require, because these many number of nodes you actually need to, on an average, navigate before you get the goal node. all are not kept in the memory all the way, but at least some of them or maximum of them are in the memory, because when you use a star, you are using graph search. जो explode और unexplode node है, दोनों अंदर रहते हैं आपके memory में. Okay, see, that's why the memory footprint is larger for the A star, because you are maintaining both the uh, fringe nodes as well as the closed list nodes in the memory. Fine. So this is how we can understand. We can always obviously see that H2 always requires less number of nodes to be inspected before you get the solution. That's how you can understand or compare different heuristics. And this is how people actually arrive at better heuristic. So what we have learned today so far is identifying a heuristic is altogether a challenging task, and to have that particular understanding which heuristic is better over the other heuristic, we need to be able to solve the problem. Then you will ask me, अगर मुझे solve ही problem करना है तो फिर why to do this kind of study? Because to better your performance, because ultimately we are talking about rational agents, so rational agents will always try to get a better option to do a solve a particular problem. Okay, so that's the whole idea behind this particular topic. Now, one way to do solve the identification of heuristics or finding better heuristics for a problem is by uh, getting the heuristics out from a relaxed version of problem. Now, relaxed version of problem मतलब क्या है? प्रॉब्लम में जो कंस्ट्रेंट है उनको थोड़ा रिलैक्स करके अगर कोई प्रॉब्लम को सिंप्लीफाई किया जाए, और उस सिंप्लीफाइड प्रॉब्लम को मैं सॉल्व करने के लिए अगर कोई ह्यूरिस्टिक प्रपोज करता हूं, because that problem is easier to solve, I can easily get a heuristic value based on my experience of solving the relaxed problem. Okay, and it has been found that cost of an optimal solution to a relaxed problem is always or is mostly the admissible heuristic for original problem. So this is the important result, that is the genesis, or that is the reason why people use this approach. So the approach is simple. Rather than solving the usual original problem that we need to find heuristic for, relax that problem a bit. By relaxing the problem, we mean maybe allowing more steps, maybe allowing more better ways to represent a state otherwise which is being required. And now if the relaxed problem is easier to solve, it will be easier for you to find out a better heuristic for the relaxed version of the problem. Okay, if I have a optimal solution for a relaxed problem using a heuristic, such heuristic is an admissible heuristic for the original problem as well. Okay, and it's a established result by people working on the AI problems. So you can rely on this kind of insights. Okay, this is not any theorem, this is not anything which can be proved very easily or intuitively, but people have actually experimented a lot, like the one that we saw earlier, and with this knowledge they have actually gained this understanding that if I solve a easy problem, easy version of the same problem, that is relaxed version of the same problem, then the heuristic that I use for solving that problem can also be a admissible heuristic for the original problem. Okay, so see, they are talking about H1 and H2. If the rules of 8 puzzles are relaxed to so that the tile can move anywhere, then H1n gives the shortest solution, because H1n notes what, how many tiles are misplaced. So I'll know 8 tiles are misplaced, so I will pick up one tile and get it to its original position. Automatically 2 tiles now are correctly placed. So initially if 8 tiles are misplaced, after one move it will be only 6 tiles which are misplaced. Second move there will be 4 tiles which are misplaced. Third move, only 2 tiles are misplaced. And fourth move, I get the solution. So in 4 moves itself, I directly get the solution. Now, what will be the branching factor is a different sort of story, but I will definitely get a shorter solution if I allowed a tile to be able to move anywhere. Okay, so it's a relaxed version of original problem. In the original problem, the tile can be only navigated in horizontal or vertical neighborhood. Okay, I can only move a tile one step to horizontally adjacent cell or vertically adjacent cell. Okay, so that is how I can arrive at H1 heuristic. Okay. Next is if the rules are relaxed so that a tile can move to any adjacent square. Adjacent square means trigonal squares as well. So I am allowing it to move in any 8 places around itself. So if this is the cell, 4 places are 4 neighborhood and these 4 other places, the diagonalities. Okay, then the shortest solution would be easily obtained using H2 heuristic. Okay, so that is how a heuristic is